I was talking to someone from Mars the other day who said, "You Earthlings, I don't get it. So you say things like this. You say that, um, let me write it. So, how, how could those possibly be equal?" And what the Martian is looking at is the difference, and there's a big difference, between writing a fraction 2/3 or writing an ordered pair 2 comma 3. And if you think about this, an ordered pair is those are equal if each of the components is equal. So this is nonsense. So let's fix that. Those are not equal, but we persist in saying that 2/3 is 4/6, and we need some vocabulary to describe that phenomenon, and so that we can make sense. They are not equal. It's a different way of writing an ordered pair. And an ordered pair 2 comma 3 is not equal to 4 comma 6. So what we mean here is that there's a relation, and the relation is, I'll do it symbolically, is A over B is related to C over D. So I'm using this congruence symbol for relation. Usually this defines the relation. And I'm going to say that these two are related if and only if AD is equal to BC. Or another way to say that is that AD minus BC is 0. So that's the cross multiplication test we use for multiplying fractions. And so what we mean is that somehow those are not the same pair, but they're the same fraction. And that's a relation. That's two things, and we're saying that there is a relation between them, that they are the same fraction rather than that they are the same thing, because they are not the same thing. So let me remind you of the formal definition. So if I have a set called A, then a relation is a subset of A cross A. Might be the whole thing. So that's a relation. And in this case, the relation does not include allowing the second thing to be 0. So this is a relation, and there's a subset of things that satisfy this, and so that's the relation. We also have the additional condition that the bottom's not 0. So people have been talking about this fraction relation for centuries without pointing something out. That's actually kind of difficult if you do it in the form of AB over CD. So I'm going to rewrite this because we're going to need this later. We need to be very strict. We need to be like a compiler in how we think about the manipulations that go into checking whether this relation is true. And so, instead of A, so I've got A over B related to C over D. I'm going to just call this TL, top left, top right, bottom right. And the condition that we're looking for is top left times bottom right has to be equal to, we need to be very strict about this, bottom left times top right. So I've made up this notation, but I explained what it is. So T is for top, B is for bottom, L is for left, R is for right. And so when we start to work with this relation, you'll find that it's a little bit easier to think about how you're manipulating the data if you think of it by position rather than by name. So there's an old joke about the Pascal programming language, which I will skip, but it's funny. Okay, so now, there are special kinds of relations, and that's what we're bumping into here. So, an equivalence relation, and that's what we're going to be talking about. It has three properties, and I'm going to say what they are, and I'm just going to kind of cartoon what they mean. It has to be reflexive, it has to be symmetric, and it has to be transitive. Just keep, those are in alphabetical order. That's the way I remember it. So reflexive means that A is related to A, for any A that the relation is defined for. And symmetric means that if A is related to B, that implies that B is related to A. So that's the symmetry. You can flip which side of the relation that you're looking at. And transitive says that if A is related to B and B is related to C, that means that A is related to C. So those are the three conditions that a relation on a set A, or which is to say a subset of A cross A, has to satisfy in order to be an equivalence relation. So let's see that this fraction relation is in fact an equivalence relation. And that now makes much more sense to a Martian or any other rational being. So here we go. No pun intended with rational, by the way. Fractions are rational numbers, but that's the deal. So, so this fraction relation, let me just write down that name. And we're still talking about it below the line. So we need to know that it's symmetric. So, so the question is AB related to AB? Now wait a second, I was just talking about A. Well, that was when I had a set whose elements were just atoms, A's. But now I have a set of ordered pairs. So when I talk about a thing in the set being equivalent to itself, everything in the set looks like this. B can't be zero. And we're asking if this thing in the set is equivalent to this same thing in the set. And if we go by top left, bottom right, that's A times B. And then we're going to subtract off bottom left by top right, that's B times A. Well, actually, that's A times B minus A times B using the commutative property of addition. And so that is 0. So we give that one a big check mark. So that relation, this fraction relation, is symmetric. For, I'm sorry, I said symmetric and I meant reflexive because I was moving on in my mind to the next thing. So for symmetry, we're given that AB is related to CD, and we want to know whether whether CD is related to AB. Now, I'm not saying what the relation is there. So I'm given an ordered pair written in a funny way, and I say that they're related, so they satisfy this kind of stuff. And then I want to know if this pair of ordered pairs is related. That's not obvious. So let's take a look at it. And so I'm going to keep to this top left, bottom right, so forth and so forth. So, so in the one that we need top left, bottom right, minus bottom left times top right. Now that's supposed to be 0, so let's check. So that's what we're checking. And top left in the one that we need is C, bottom right is B, minus bottom left is D, top right is A. We're pulling these by position. It's almost like, you may not have done much assembly language programming, but someday you will. It's almost like you're specifying memory addresses here. So TL is a certain register. BL is a certain register. And so this is a very computational manipulation that is related to the way we do many other kinds of computing. Okay, well, let's go back to, we're supposed to have this thing being equal to 0, and we're almost there because C times B is B times C, and D times A is A times D. So those are properties of multiplication. And so this is the negative of AD minus BC, and we're given that AD minus BC are 0. So this is the negative of 0, which is 0, unless you're doing one's complement arithmetic, which don't do that. in one's complement arithmetic, which is a machine architecture question, there are 2 zeros. Don't do it. Okay. We use 2's complement. There's only 1 0. So what we've done is we've taken, this isn't like any other proof, we've taken what we need, and actually the reasoning goes the other way, but we were able to do the manipulation. What we wanted to calculate this thing and see that it's 0, and we plugged in the data and we did some manipulations involving the larger set, the properties of addition and multiplication, and we got 0. So that proves that this is 0. Okay. The transitivity one is, man, it's hard to get this right the first time. So let's write down what it is that we're trying to say about transitivity, and then we'll show that in fact it happens. So we're given that A over B is related to C over D, and we're given that C over D is related to E over F. And what we need is A over B is related to E over F. So that's the transitivity condition. I've got things that are equivalent, and the second one here is equivalent to yet another one over here, and that means that the first and the third are in fact equivalent. So given that we're working with ordered pairs, we write down ordered pairs, and we come up with this condition here. So what we need here is, well, let's see, we need top left, bottom right, minus bottom left, top right to be 0. So that's the condition in this fraction relation. And so in the one that we need, we've got that is equal to AF minus BE. And I'm sticking to the conditions strictly. Top left. Okay. So I need this AF minus BE to be 0. And there's a trick, which is this. And so now this is the math part. This isn't the logic part. This isn't the reasoning part. This is the math part. And this is one of those kind of creative things that you have to bring to bear. If I multiply by C, which is, I'm sorry, if I multiply by F, it's good to multiply by F because I know that F is not 0 because we can't allow 0 on the bottoms of these things. That's part of the condition defining the set or the relation. So F is not 0, so I can multiply through by F. Oh, I wrote down the wrong thing. Oh, demon sacks have used macaroni. I guess I'm multiplying through by C. Okay, well, let's see what happens. I've got ACF minus BCE, and I'm taking advantage of the commutativity of multiplication. And the thing is that we're given, because of this, that CF equals DE. So I can make that substitution. So this is ADE. And we're also given, well, we'll just stick to BCE for a moment. And now I've got, using the distributive law, I've got AD minus BC times E, and we were given that that was 0. So that means that the composed ordered pair satisfies the condition to be in our relation, and therefore the relation is transitive. So I'll just give that a check mark just to be clear what's going on. So that's what we have to tell the Martian. No, they're not equal. They're equivalent in this fractional relation. And so that is now perfectly legitimate, and the Martians go home and don't invade us. Okay. So now there's something else that goes on here, which is that, 2/3 is 4/6, is 6/9, and so forth and so on. So there are a whole bunch of fractions that are equivalent to 2/3, And if they're each equivalent to 2/3, then they're equivalent to each other. And so every pair that doesn't have 0 on the bottom has a whole set of things to which is equivalent. So the equivalence class is the name of a set like that. The equivalence class of some x in some relation is, well, the standard notation is to put x in square brackets. And that is the set of y with the property that y is equivalent to x. So the fraction one's kind of, it's too big. So if we look at a different example, let us look at integers mod 3. So the equivalence is there related if their difference is divisible by 3. So there are 3 classes. There's the class of 0, there's the class of 1, and there's the class of 2. And you find the class of x by a remainder when you divide by 3. So the class of 7 is the class of 1, and so forth and so on. The class of 3 is the class of 6, is the class of 129, is the class of 0. So there are a lot of different ways of specifying a class, but there are only 3 classes. And the 3 classes have an important property that is true of every equivalence relation, and something that we've seen before. The equivalence classes form a partition. It seems to be like that's a long sentence to write, excuse me. They form a partition. So remember, a partition of a set is a bunch of subsets that don't intersect, they're disjoint, but everything is in one of them. So you can go back and look that up, but so a partition, so A is the disjoint union of a bunch of sets, we'll call them S sub I, and S sub I intersect S sub j is empty unless the 2 sets are equal. That's not exactly how we said it before, but that's how we should have said it before. So in a partition, the sets either stay apart or they're the same. So, and that's what's true with these equivalence classes. If you divide something by 3 and the remainder is 0, then you don't divide it by 3 and the remainder is 1, and so forth and so on. So the equivalence classes of that mod 3 partition of the integers form a partition of the integers, and that's true for every equivalence relation. So if you have an equivalence relation, you form the equivalence classes. Now they have many different names, but there are just a few sets that have the same name, and then the equivalence classes form a partition. Conversely, if you have a partition, you can define an equivalence relation by x and y are equivalent if they're in the same set. So I spelled partition wrong. Partition defines an equivalence relation. So first of all, it defines a relation, but that relation is in fact an equivalence relation. So I'm going to use just a tilde for the relation symbol. X is related to y if and only if they're in the same set. And so that's true for every partition that you could imagine. And so, well, x is in the same set as x. If x and y are in the same set, y and x are in the same set. And if x is the same set as y and y is in the same set as z, then x is in the same set as z. So that's one of the simplest ways to define an equivalence relation is to be given a partition. So that's the deal. So one way to think of it is that we've partitioned the ordered pairs that don't have the second one 0 using this fraction relation that forms a partition of the ordered pairs of integers where the second one isn't 0, or taking integers modulo 3 or 7 or 2 to the 33rd plus 1. That's a much more interesting one. That has applications in cryptography. So you take integers mod whatever, and you get that number of equivalence classes. Integers mod 4 have 4 equivalence classes. Integers mod 10 have 10 equivalence classes. Those form a partition, or you could take a partition and use that to define an equivalence relation. So those are closely tied up concepts. You can't have one without the other, and so that's the deal. So everyone on Mars is happy, everyone here is happy, and so we'll be happy.